So this is called, title is Relative Property T for Nilpotent groups. I thank the organizers for inviting me, and I'm very happy to be here for the first inaugural AOWM meeting. We are all, many of us are ambassadors for CWM and hence for AOWM. And anything related to women in mathematics is very close to my heart, and I'm glad to see that this conference and AOWM will take it forward. And I'm happy to see all the young people who would take this cause forward and support each other and other women students and postdocs. And so you have all seen my abstract, so I'm not going to repeat it. This is joint work with Indira Chatterjee and David Morris. So this is the plan of my talk. I will introduce Kazhdan's property T and then relative property T. I'll give some examples, then main results, consequences of these results, and relative property T for triplets and Kazhdan sets. So these triplets are not the usual triplets. They are not born at the same time. It's about a group and a subgroup and another subgroup. So they are different. So I usually work in, well, to start with, I worked in probabilities on groups, and then I do dynamics of group actions, and then anything which I can use any of these things in it, or anything else that I can learn and do. So this is a one-off thing which I learned when Indira Chatterjee was 1 year NBHM visiting professor at JNU. That's when I learned, and then we worked for a few more years, and I used this. And believe me, other things like dynamics also is useful here. So all my groups are locally compact, and so if G is a locally compact group and pi is a unitary representation on G on a complex Hilbert space H, for a compact set K of G and epsilon greater than 0, we say that the unit vector psi is K epsilon invariant if pi G psi minus psi is less than epsilon for all G belongs to K. So these are K epsilon invariant vector. For you, it's a unitary representation is a representation of G with imaging bounded linear operators on GH. And the image is unitary. So unitary means it preserves the inner product. So it's a unitary operator for each. Okay. So we say that pi has almost invariant vectors if pi has K epsilon invariant vectors for every compact set K in G and every epsilon greater. So everybody knows what is locally compact group, right? It's locally compact in its topology, and it's a topological group. So you can think of linear groups, okay, closed subgroups of GL and R. That's a large class of examples, even for Lie groups, but not all Lie groups have this form. A group G has Kazhdan property T if every unitary representation pi that has almost invariant vector has an invariant vector. Okay, so that means if it has these K epsilon invariant vectors for every epsilon greater than 0 and every compact set K, then there must be a vector psi which is kept invariant under this unitary representation. That's pi G psi is psi for every G in G. So this was introduced by David Kazhdan in 1967. It's a very short paper, like 3 pages. And Kazhdan's aim was to study the structure of lattices in a Lie group. He wanted to prove that lattices in a simple group of rank greater than 2 are finitely generated. So for example, SL3R, SLNR. So what is a lattice? Lattice is a discrete subgroup of a group, topological group, locally compact group, such that quotient is either compact or it carries a finite G-invariant measure. That's lattice. For example, SLN-Z is a lattice in SLN-R. Zn is a lattice in Rn. He shows that the simple groups of rank greater than 2 have property T, and then he shows that the property T is inherited by lattices, and then he shows that all discrete group gamma with property T are finitely generated, and its abelianization gamma by gamma gamma is finite. So what is gamma gamma? It's a subgroup generated by commutator. It's called commutator subgroup, right? A, B, A inverse, B inverse generates a subgroup. That's your gamma gamma, where A and B are in gamma. In general, any locally compact group with property T is compactly generated, and its commutator subgroup is co-compact. That's like G by GG is bar, it's compact. So its abelianization is compact. Now we define what is called relative property T, because it's a more general concept and it's very useful. Let H be a closed subgroup of G. Then we say that the pair GH has relative property T if any unitary representation pi of G that has almost invariant vectors is restriction to H has invariant vectors. So the whole of G may not have an invariant vector, but the subgroup will have invariant vectors. This was implicitly introducing Kazhdan's that first paper for a particular pair SL2R semi-direct product R2, R2, and later defined explicitly by G.A. Margulis. Margulis is the famous field medalist, you know. So G has property T if and only if G has relative property T, right? So it is easy to see that if G has relative property T, then GL has relative property T for any subgroup L of H. And so often you can use this to prove whether group has property T or not. So G has relative property T if and only if for any closed normal subgroup H, GH has relative property T and the quotient has property T. So relative property T was used by Kazhdan to prove property T for SL3R and Margulis to study finite additive measures on Rn. And he also found families of expander graphs with the use of these relative properties. So all compact groups have property T, okay? SLNR for n greater than or equal to T, 3. This has property 3, but SL2R does not have property. SL2Z semi-direct product Z2 has relative property T. And if GH has relative property T, then so does G by L, H by L, where L subset H is a closed normal subgroup. For the quotient, you can get easily because if you take a unitary representation of quotient, you can extend to the unitary representation of G by just taking the projection map and composing it, right? So you can do that. And if H subset G and H has property T, then by Mautner's phenomena, you can show that HCH also has property T, where CH is the closed subgroup generated by contraction groups of these H belongs to H, which is defined like this. So their intersection for every H belongs to Hn, G, H to the power minus n, the conjugation of action of H on element G converges to identity as n tends to infinity. So now let's see some non-examples. Any group which is not compactly generated does not have property T. For example, SL and Q with discrete topology, it's not compactly generated. Q itself is not compactly generated, right? If you take discrete topology, when you say compactly generated, you have to say finitely generated, because compact subset of discrete space are finite. SL2R does not have, and in turn SL2Z, which is a lattice in SL2R, does not have property T. SL2R semi-direct product R2 does not have property T. SL2Z semi-direct product Z2, SL2Z semi-direct product. Any non-compact amenable groups. So what are amenable groups? Amenable groups are the ones which have invariant mean. So it's a finitely additive probability measure on that. Or you can equivalently say that if you take L infinity G with respect to the Haar measure on locally compact group, and you have a positive linear functional on it, which is G invariant. So all nilpotent groups are amenable, and any connected group which is amenable is a compact extension of solvable group. But they are not, so all solvable groups are not amenable, but any compact extension of amenable group is amenable. So any group G such that G by GG bar is non-compact doesn't have property T, because if G had property T, its abelianization must be compact. So for example, you take free groups with two generators, right, which is contained in a set. So the quotient is going to be Z2, so it is not going to have property. It doesn't have property T. So if GH does not have relative property T, GH does not have relative property T if the image of H in its abelianization G by GG is non-compact. Okay, so if you're an abelian group, the relative property for the subgroup, then the subgroup must be compact. So relative property T has applications too. These are some of the things that I'm listing, but there are more. Ergodic theory, geometric group theory, lattices in algebraic group, expander graphs, theory of networks, operator algebras, and representation theory. The following result is due to Serre, Serre, the famous mathematicians many of you may have heard of, for central extensions. So what is the theorem? If C is a closed central subgroup of G such that G by C has property T, then G1 equal to GG bar has property T. GG bar is the closure of the commuter subgroup. Moreover, if G by G1 is compact, then from that characterization, you can say that G has property. So many results, many groups with property T are proven like this. So we generalize Serre's result to the following main theorem. So let H be a closed subgroup of a locally compact group G, and let A be a closed subgroup of the center of H, such that A is normal in G. And if G by A, H by A has relative property T, then G by H1, which is a commutator subgroup of H, has relative property T. Moreover, if H by H1 is compact, then GH has relative property. So this is a special case where A is central in all of G and not merely in H. The special case where A is central in all of G and not merely in H is a generalization of a result by Cornelier, as he assumes additionally that A is contained in H1, where H1 is the commutator. So Serre's proof uses a tensor product of pi and pi bar, which is trivial on the center when pi is irreducible. You can work with irreducible, it's enough. So while we use tensor product that is fibered over the eigenspaces of the abelian normal subgroup A, because A is not central in G. And this is derived from there. So let N be a closed nilpotent normal subgroup of G. What is a nilpotent group? Nilpotent group is you take commutator central series N, which is N1, N2 is N1, commutator of N and N1, and so on. This central series must end in finitely many steps to identity. For example, you take strictly upper triangular matrices in GL and R, it would be, the last part will be center, and it just keeps going above diagonal when you take this. First diagonal, second diagonal, they become trivial. And finally, the last one is the center. So here, as I mentioned, and in the abstract also, it's called abelianization of group N, which is N by N1, because N by N1 is abelian subgroup, abelian quotient. So theorem 2 can be proven used by using theorem 1 and the induction on the length of central series, right? Because if you start with length 1, then it is an abelian group, so you can apply the main theorem and then you can use the induction. So Cornulier and Tesra have characterized precisely when the pair H semi-direct product A, A has relative property T for an abelian group A. Okay. So theorem 2 yields a characterization of pairs for pairs H semi-direct product N, N, where N is nilpotent. See, you have results for N by N1, which is abelian, but that implies relative property T for Gn. Then you can use these results. You can say generalize these results for abelian to nilpotent. So the following is a special case that is in a particularly usable form, and it's based on the work of Cornulier and Alan Wallet. So let me put some notations. So if you have H invariant normal subgroup L of N, and then we have a map H acting on conjugation on N by L. So it goes into automorphisms of N by L. So you take the closure of the image, which is called int N by L H or star bullet, be the closure of the image of H. So that's the, so suppose H acts on a one connected nilpotent Lie group N. The pair H semi-direct product N, N has relative property T if and only if for every close connected H invariant proper subgroup L of N that contains N1, the group int L N by L H bullet is not amenable. So one connected is just simply connected. It's pi fundamental group pi 1 of that group is N is trivial. So for example, your strictly upper triangular matrices or any group which has a faithful representation to GL and R falling into strictly upper triangular matrices. And it's equivalent to say that it has no non-trivial compact subgroups. Okay. So all the quotients are isomorphic to Rn. The center is isomorphic. And any connected nilpotent group, you go modulo maximal compact central subgroup, it is simply connected. More generally, we have the following corollary. So this is, what it says is that not just this property T, but you can find a unique largest subgroup L dagger in a subgroup N such that G L dagger has relative property T. So you have a N which is locally compact nilpotent normal subgroup, which is a compact extension of its connected component. Then N has the largest subgroup L dagger, say, such that G L dagger has relative property T. Furthermore, so there is no other bigger subgroup than L dagger. L dagger is a closed normal subgroup of G, no bigger subgroup where you get this relative property. And the quotient N by L dagger is a one connected Lie group. And in this int L N by L dagger G star is amenable. Okay. So this is, the compact part always go into which is group with relative property subgroup, because if you have a group G and compact subgroup, H, then GH always has relative property T, because H has property T. And this is another corollary which says let N be a closed normal subgroup of a locally compact group G such that N1 is nilpotent, then Gn has relative property T if and only if G by N2, N by N2 has relative property T, where N2 is N1, N1 bar. You may recall that if you have a connected solvable Lie group or connected solvable locally compact group, its commutator subgroup is always nilpotent. It's contained in the nilpotent. So this corollary will apply to solvable connected subgroups of locally compact. Okay, because its commutator subgroup will be nilpotent. Suppose N is a closed normal subgroup of a locally compact group G such that N is a connected Lie group, then you can characterize these maximal group with relative property T in this sense. So S is the product of non-compact simple factors of Levy subgroup. So any Lie group has a Levy decomposition, which is G equal to SR. S has two parts. There are compact simple factors and non-compact. So you take all non-compact simple factors because compact doesn't matter in terms of property T. And then let U be the nil radical of N. Nil radical is the maximal connected nilpotent normal sub. Okay. Then Gn has relative property T if and only if S has to have Kazhdan property T. N by SU bar is compact and G by U by US has relative property. So this is sort of maximum thing you can get for relative property T for Lie groups. So now, as I said, we'll talk about relative property T for triplets. So here the triplets or even relative property T is defined for subsets also, not just subgroup. But it is suitably modified for subsets, and it's also a useful thing. We never thought of doing it for subset, but then referee asked, what about subset? Because there's a lot of work. So we added one more section and it is much more complicated for subsets. So it's a generalization of subgroups, but still. So let H be a closed subgroup of G and M is a subset of G. Then GHM has relative property T if for every epsilon greater than 0, there exists a compact subset Q of H and delta greater than 0 such that every unitary representation of G with non-zero Q delta invariant vectors also has non-zero N epsilon invariant vectors. So here it doesn't say that there is an invariant vector, but it's true for every epsilon greater than 0. And let me mention this, that if M is a closed subgroup, it is equivalent to saying that M has an invariant vector. So let H, M, so this is by Paul Jolisa. Let H and M be closed subgroups of G, then GHM has relative property T if for every unitary representation pi of G, such that pi restricted to H has almost invariant vectors, then pi has M invariant vector. So you see, this is more general than just relative property T, okay? Because you expect almost invariant vectors not for G but for H, which is just any subgroup. And M is also not a subgroup of H. M is any other subgroup. But that is where dynamics plays role. So these definitions generalize the definition of relative property T for pair GM, where M is a subset or closed subgroup, as one can put H equal to G and GGM as relative property T if and only if GM has relative property. So you will see next why often this can be done, like what Kazhdan did for SL3R, he did SL2R semi-direct product R2, and then you actually look for all that elements on which it acts by contracting it and then showing that that becomes a dense subgroup of SL3R. So let H and M be closed subgroups of G such that M is normal in G, and a subset M be a closed subgroup which is central in M and normal in G. And if HA is closed, then G by A, HA by A, M by A has relative property T, then G, H, M1 has relative property. This theorem helps us to generalize some results of C.R.E. Raja on strong relative property T for groups of type G equal to H semi-direct product M to all pairs HM which has strong relative property T, H which acts on compactly generated nilpotent subgroup M. So strong relative property T just means that your G is of this form H semi-direct product M and GHM has relative property. Now that action helps you get it on the whole space. There is an analog of theorem 3 for subsets, but we will not go into that because I'm running out of time also, and I thought I will tell you something more interesting in the next slide. So this is one corollary of that result. Let A be a closed abelian normal subgroup of a locally compact group G, and H is a subset of G that centralizes A. Let this double bracket HH is a commutator set for H as defined. If G by A, HA by A, now HA by A is just any subset of G by A, is a subset of G by A, has relative property T, then GHH as subset has relative property. So, I mean, it may be difficult to check for every set K epsilon invariant vectors and so on, right? It turns out that if a representation has almost invariant vectors, then there exists one epsilon greater than 0 and one compact set such that so a group which has property T if and only if there exists one epsilon greater than 0 and a compact set K of G such that every unitary representation of G that has K epsilon invariant unit vector has a non-zero unit vector. And this compact set K is called a Kazhdan set for G. There could be more, right? If I take a larger one, it will also be sometimes. And a small, bigger, slightly bigger epsilon. So a pair, similarly, a pair GH has relative property T if and only if there exists an epsilon greater than 0 and a compact subset K of G such that every unitary representation of G that has K epsilon unit vector has a non-zero H invariant vector. So here K is called a Kazhdan set for the pair GH. Now, this was one of the applications which I'm just putting as remark of some of our results. If Q is a subset of a locally compact group G and A is a closed abelian normal subgroup of G such that image of Q in G by A is a Kazhdan set for G by A, and every G invariant finite measure on the dual of A supported on the set of fixed point of G, then Q is a Kazhdan set for the pair G1 where G1 is a commutator. As I mentioned earlier, the results presented here are from a joint work with Indira Chatterjee and David Morris. It appeared in Documenta Math in 2018. And any reference you can find in this paper. Not only that, the paper is somewhat technical. So the version on the archive has few pages notes which you can see to explain smaller results. And there are many more applications and results in the paper. Of course, I cannot go through all of them. This is just a gist of main results in the paper. Thank you very much.
There is a question in the chat. It says that any relationship between H and M.
H and M, where? No, they are independent of each other.
Okay. Are there any questions from the?
So many groups now, people are using new techniques and finding actually Kazhdan sets. Yeah, and so our work has also had some applications in these Kazhdan sets. There is a paper, I can't pronounce their names and I don't remember, but you can see it because it came out around the time and then they saw and then they put some more things. So, but there is a way of quantifying these, but not for every group. Okay, it's just existence, but not for it.
For some cases, it may be known explicitly.
Yes.
For example?
No, I don't remember the example because it came out recently. So, but if you have action of H on M, it might be a, if it's a connected group, it would be some compact group, compact set, which is generating the H. So,
are there any more questions? If not, then
every unitary representation of G which has an K epsilon invariant unit vector has a non-zero H invariant vector, but that need not be unique, right? Or is it unique?
no, because I mean, if psi is invariant, alpha psi is also invariant, and not unique. No, there could
Not
be
unique.
more.
There could
like
be other types.
that could be many. Yes,
Okay.
but at least one. So
Yeah,
sometime you can. So to do on quotient, what you'll do is you take that. So it means that trivial representation is weakly contained in the in L2 in this representation pi. Okay? And it also means that when you take Feld topology on this set of unitary representation, identity is an isolated element.
So, if there are no more questions, let's thank the speaker for a really nice talk.
Thank you. And I'm here till Friday, so you can bug me whenever you feel like. Anything you want to ask me, I am open to questions. I gave I worked few years ago, but okay. It's always good to go back. And in fact, I'm thinking of starting to work on this again. There are lots of open questions. Thank you.